Okay, Assalamualaikum warahmatullahi wabarakatuh. Today we will learn about physics. One of the best topic is electromagnetic induction. So I have my friend, this is Alya, this is Amir. Okay, so let's start. We start with our intro. Okay.
Assalamualaikum warahmatullahi wabarakatuh. Today, I will explain about one of the best topic in physics, that is electromagnetic induction. This topic consists three subtopics. The first subtopic is induced electromagnetic force (EMF). I will explain the first topic. My friend will explain the another subtopics.
Okay, so I will explain the first topic, which is induced EMF. Okay, inside this topic, there are four topics that we need to learn. The first is the induced current and EMF. Second is magnetic flux. Third is Faraday's and Lenz's law, and the last is motional EMF. So now I will explain about the first topic is induced current and EMF. Okay, for the Faraday experiment, okay, when Michael Faraday made his discovery of electromagnetic induction in 1851, he hypothesized that a changing magnetic field is necessary to induce a current in a neighboring circuit. To test his hypothesis, he made a coil by wrapping a paper cylinder with wire. He connected the coil to a galvanometer and then moved a magnet back and forth inside the cylinder. So this is the magnetic coil experiment. So the current is induced when there is a relative motion between the magnet and the coil. Okay, so if I move this magnet to the coil, the galvanometer will deflect. And when I move away the magnet from the coil, it will deflect reverse. But if I increase the magnet speed to the coil, it will deflect more. But if I move away this magnet from the coil with a speed, it will deflect reverse with speed. So now let's start with the second part, which is the magnetic flux. Magnetic flux is proportional to both the strength of the magnetic field passing through the plane of a loop of wire and the of the loop. So we can define as the magnetic flux as P equal BA cos theta. What is B? Okay, B is the magnetic field, A is the area of the current loop, and theta is the angle between the direction of B and A. Alright, so the unit for the magnetic flux is Weber, WB. So now we focus to our next topic, that is Faraday's and Lenz's law. This law have their relationship. So Faraday's law states that induced EMF in a circuit is proportional to the rate of change of magnetic flux through the circuit and may be increased by the number of wound loops N. So the formula they said is EMF equal N times by delta magnetic flux over delta time. But with Lenz's law, we can add negative sign so it can show the direction. Easy. So finally we go to our last subtopic is motional EMF. EMF induced in the conductor moving through a magnetic field is called motional EMF. Okay, so the induced EMF called motional EMF. So this topic have different formula. The first formula is EMF equal to magnetic field times by length times by velocity. For the second formula of the induced current is induced current equal EMF over R O equal to magnetic field times by length times by velocity over resistance. So I think that's all for this video. Now I will pass to my partner Alya who will explain the next subtopic. Bye.
Thank you to Amzar for explaining subtopic 1, which is induced EMF. Now let's continue to subtopic 2, which is self-induction. So what is self-induction? By the subtopic itself, you can actually know what it means. Self, just remember by yourself. So self-induction, it happens in inductors or a solenoid. So like I said before, self, by yourself. It means that the solenoid produces induced current or induced EMF by itself without the help of anything else.
So I have a solenoid. Hello, I'm solenoid. My solenoid is very happy because she has an AC power supply, which means that she has current flowing inside her. When you have current flowing inside a solenoid, there will always be a magnetic field. To determine the direction of the magnetic field, you have to use the right hand grip rule. So now what you have to know is, how does self-inductance occur? It occurs when you either increase the current or you decrease the current inside the solenoid. Let's start with increasing the current. When you increase the current, your B also increases. So the solenoid will be mad. It doesn't like this change. So it will produce an induced current opposing the direction of the current inside the solenoid. Therefore, when you have an induced current, there will also be a magnetic field, which the direction of the magnetic field will be opposite to the direction of the magnetic field for the current, not the induced current. Now I have my friend Hulk here to help me tidy things up. Thank you, Hulk. Bye. So next, what happens if we decrease the current inside the solenoid? The B also decreases and it makes the solenoid really mad. Like, it doesn't like this change and it will try to increase the current by inducing a current in the same direction as the current inside the solenoid, and it will also produce a magnetic field in the same direction as the magnetic field in the solenoid. So this is what you call self-inductance. As you can see, when you increase or decrease the current inside the solenoid, it will produce the induced current by itself without the help of anything else. That is what you call self-inductance. You can pause this video to help you understand better.
So the next thing that you should know is, what is physics without a formula? So let's just explain this formula. This is the formula that you need to remember. There are two formulas. This is the induced EMF. Induced EMF is equals to L delta I over delta T, and also L, which is inductance, equals to mu naught. Mu naught is a constant. N squared, which is the number of turns or the number of coils. N is the number of turns or the number of coils. A is the area, and the small l is the length of the solenoid. So the unit for inductance, L, is Henry. H. So how you need to remember, a very easy way is to remember HL. Remember the milk, HL, and you'll definitely remember this one. So for the last part of this subtopic, you should know that inductors stores electrical energy. So the EMF induced by an inductor, it prevents a battery from establishing an instantaneous current in a circuit. So the battery has to do work to produce current, and you should know that to do work, you need energy. That's when this formula comes in handy. Ta-da! This is the formula for energy. So this is the formula for energy in this subtopic. It is just 1 over 2 L I squared. I is the current and L is the inductance. So that is all for the second subtopic. Let's move on to the third subtopic, which will be explained by Kiran.
So thank you Amzar for explaining about the EMF and L about the self-induction. So now let's proceed to the my presentation, which is about mutual induction. So mutual induction is the actually basic principle for transformers and type generators such as AC to work. So let's get to know about how mutual induction is going to be applied on transformers. and how these two topics, which is mutual inductance and transformers, affects. So the first thing is we should know is that mutual inductance. So mutual inductance is actually a basic operating principle of the transformers, motors or generators. Basically, AC type generators effects, such as we have two equation here, which is for primary and secondary coil. So of course, the first primary coil will produce magnetic field and will affect the current and leads to induced EMF in the secondary coil. So inductance in both coil is actually mutual, and the current flowing of one coil induce voltage in an adjacent coil. So this principle is applied on the transformers. As we have learned before, we have two types of transformers, which is the step up transformers and step down transformers. So what is the difference between both transformers? The difference is that the number of secondary coil in step up is greater than in the step down transformers, and of course the greater the number of coil in the secondary coil will determine the output voltage will going to be greater, and the output voltage will become lower in the step down. And for information, the current in the step up is low, while the step down the current is high at the both secondary coil. So what actually we use transformers in our life? We learn about this in our high school until now, but what is actually the application of transformers? So the basic application of transformer is that our national grid network, which is from the power supply from the hydroelectronic generator that we supply to the step up transformers, and we're going to increase the voltage up to 275 kilovolt and will be supplied to the grid network and until it comes to the step down transformer. So why we use step up transformers in the first place? It's because we want to reduce the current so that reduce the energy loss during transmission from one location, which is power supply, to area that we're going to distribute the voltage energy. So from the step up transformers and from the grid, we're going to depend at the step down transformers. And the step down transformers, we're going to lower down the voltage to the grid up to 132 kilovolt, and we were going to step down once again up to 240 volt, so that we can distribute to the houses of the resident in our time, not too dangerous, and it is applicable to our electrical equipment such as houses and industry places. So I think that's all from my explanation about mutual induction. So basically what you need to learn to understand about mutual induction is because mutual inductance is the basic principle of the generators, so that the transformers can work. And so when transformers, we can apply the transformers to work, we can use the transformers to give us a greater amount of voltage to produce and make our lives easier, like now. So that's all from me. Thank you.